Hey guys, Buildzoid here, and today we're going to be taking a look at the MSI MPG Z590 Gaming Force motherboard. Now, this board uses exactly the same PCB as the gaming carbon Wi-Fi. There's like a carbon board, it costs more, it's the same board, except that it has the Wi-Fi module over here. This doesn't have the Wi-Fi module, which makes it superior, because that's a Wi-Fi 6 module, and Wi-Fi 6 is pretty expensive, so... You know, like, you save quite a bit of money by going with the Gaming Force instead of the Carbon Wi-Fi, which, in my opinion, like if you're not going to use the Wi-Fi, that's a pretty good idea to just not pay extra for the expensive Wi-Fi 6. So, yeah. Anyway, then the rear I/O is the same as the Carbon Wi-Fi. So you've got BIOS Flashback, so you can update the BIOS of the motherboard without even having a CPU installed. We've got some USB 2.0 ports. Display outputs, more USB ports, 2.5 gig Intel LAN, the blank spot where the Wi-Fi would be, and some more USB ports. Also, there's audio outputs, which, you know, motherboards have. You can tell I don't care about the rear I/O. No, the reason I've decided that I wanted to do a PCB breakdown about this motherboard is because of this right here. This is MSI's cheapest Z590 motherboard to come with a postcode. The postcode is, like, as far as I'm concerned, pretty much the defining feature of an overclocking motherboard. If you don't have a postcode, memory overclocking is just generally very unpleasant. And so this is super, super handy to have, especially on Intel, because, like, on AMD motherboards, most of the time you just kind of get an F9 code, and there's not much you can do about it. On Intel motherboards, you can get quite a variety of different postcodes indicating various issues. So, yeah, this is actually really, really handy. Now, other than that, we've also got what looks like color-coded troubleshooting LEDs. I can't actually get, like, I didn't manage to get confirmation that they are color-coded. Either way, they're kind of redundant considering that you do have a postcode up there, so, you know, yeah. But if they're color-coded, that's awesome because you can tell at a glance what's wrong, and if they're not color-coded, well, the postcode is the superior method of troubleshooting anyway, so I don't really care that much about the LEDs anymore if you got one of these. Other than that, there's also a hole in the CPU socket for putting a K-type thermocouple through. This is the idea behind... There's very few people... I don't know many overclockers who actually use this. I know there's definitely some that do. It's just, I can't think of anybody off the top of my head that actually uses this. But the idea behind that is that you can put a K-type thermocouple through it and, like, stick it to the back of the CPU, and you can monitor, like, what state your thermal paste is in on LN2, because the thing is, when you're on LN2, the regular temperature sensors, they don't work anymore, so you need to get, like, a K-type thermocouple to the back of the CPU. Well, you're going to need a hole in the CPU socket like this, so that's what's going on over there. And yes, this motherboard actually would be totally viable for extreme overclocking. There are obviously boards that would make the experience easier, but this is a motherboard that would be totally viable if you wanted to. So it kind of makes sense to include that on a board like this. Then we've got a clear Cmos jumper down here. So, you know, if you have the board in a case, you might want to wire that up to your reset button so you don't have to take off the side panel every time you screw up your settings. Though this is an MSI motherboard, and it doesn't come with safe boot, and it doesn't come with, like, a retry button, and I don't really have a problem with that on MSI boards as much as I do on, say, Gigabyte or Asus motherboards, because Gigabyte and Asus motherboards, you punch in the wrong settings and they just don't post. They don't post, and they don't recover. Not reliably anyway. I mean, technically the Gigabyte BIOS does have a recovery message that I've managed to trigger a few times, but the problem is it's unreliable. So a lot of the time you just end up having to hit the clear CMOS button, and the same is true of Asus motherboards. So, you know, on those motherboards, I really, really want to have a safe boot button because it makes life so much easier. But MSI boards are generally really aggressive on their auto recovery, as in, if you punch in settings that don't work, the board will just give up on them pretty quickly in, like, one or two boot... you can actually adjust how many times the board will try to boot your settings, but if you just leave it on auto, it'll try it like 1 or 2 to 3 times. And also on Intel, it does this very quickly. And then it'll just throw you back into the BIOS with all your settings still there. So if you're like me and you don't, you know, do a great job of keeping up with saving profiles and that kind of thing, you don't have to start over. Like, you don't lose a bunch of progress when you're overclocking every time you screw up one setting. So yeah, it would of course be better if this motherboard had safe boot, because it's just like the greatest button to ever be put on a motherboard as far as I'm concerned. But MSI motherboards do get a pass from me on not having it, because they also just recover really, really well, especially Intel MSI motherboards. The AMD ones, not so much, but the Intel MSI boards, like the auto recovery, because the Z490 Unify has a safe boot button. Or more like safe boot jumper. I barely ever used that. Like, I feel like I used it more to prove that it works rather than because I actually needed it. Which is definitely not true of, like, say, my other, like, say, Gigabyte or Asus motherboards that I have, where the safe boot button actually, like, the safe boot button on, say, my Gigabyte Tachyon and my Asus Apex boards, it gets more use than, like, any other button on the board, because it's just like, yeah. So I guess, yeah, just it gets more use than any of the other buttons, because, like, the other buttons are there, like, well, the safe boot button is, like, because if it were, like, because normally you just go to the BIOS, you save and reset, and then it reboots, right? And then once you're in the OS, you just use the restart from the OS. You don't need to use the power button for any of that. So, yeah, anyway, you get the idea. So, yeah, MSI does not, unfortunately, have a safe boot, but it's not, it's not really a big deal, in my opinion. And, you know, if you do have the board in a case, you might want to hook up the clear CMOS button to your reset button. Other than that, we've got a 6-pin power connector down here. I have no idea what it's doing on this motherboard, because this board does technically have the necessary PCIe switches to do X8 and X8 on the PCIe slots. However, it does not have an SLI license, so I'd love to know what exactly you're supposed to put into these PCIe slots that's supposed to, like, put enough load on the 24-pin that this would be justified. But this is the thing with MSI boards, and, like, for whatever reason, MSI seems to have a really, really hard time just putting the auxiliary PCIe power onto boards that actually need it. Because, for example, the X570 Godlike, which does have the PCIe slot spacing for 4-way crossfire, doesn't have extra PCIe power. This board right here, which technically you could run 3-way crossfire on this, I don't know why you'd want to do that. But this doesn't do, like, this board doesn't even do SLI. And it's like, you know, which, like, the only modern GPU that you would want to run several of is, like, the 3090, which, guess what, needs an SLI license. This doesn't have an SLI license, so it's like, what's this doing here? So anyway, but yeah, that exists. It doesn't hurt the motherboard by existing, of course, but I have no idea why it's here. So yeah, that's a thing. Then we've got an LED switch, so you can turn off all the RGB on the motherboard without having to do it through the BIOS, which I think is kind of neat. If you don't like RGB, you can just turn it off and, you know, not worry about it, like, through BIOS updates or whatever. So yeah, that's neat. And that's kind of that for sort of neat features, I guess. I mean, yeah, like, the main highlight for me with this board is cheapest motherboard from MSI with a postcode. Right, if you like the MSI BIOS, and I will say that, like as I said, like, the auto recovery that MSI has is great. I think also their BIOS layout is the most reasonable of all the motherboard vendors. Yeah, like, their BIOS, in my opinion, is just the best organized. So yeah, if you want an MSI board with a postcode, this is basically the cheapest option. Which, yeah, that's why we're covering this board. Anyway, other than that, there's also worth noting that this M.2 slot only works with 11th gen CPUs, because Intel just, you know, does, like, I don't know why it is that all the mainstream CPUs just don't have many PCIe lanes. Like, Ryzen has 20 usable PCIe lanes, because, and I know people are going to be, no, Ryzen has 24 lanes. 4 of those go to the chipset. Last I checked, I couldn't rewire those to a GPU or anything, so those don't count. But yeah, with Intel, it's sort of the same situation. So, like, Ryzen, you've got 20 usable lanes, 16 for your GPU, 4 for a dedicated M.2 slot. With 11th gen, you've got the same thing from Intel, where it's like you have 16 lanes to your PCIe slots and then 4 lanes for the M.2 slot. But with 10th gen CPUs, you only had 16 lanes total, and all of those go to the PCIe slots. So technically, you could run like an M.2 SSD card on the second PCIe slot and like start losing GPU performance, depending if you have like a 3080 or a 3090, there are, you know, workloads out there where if you run the card at X8 3.0, you do start losing almost significant amounts of FPS, like anywhere from 1 to 10%. Or more like 0 to 10%, because, yeah, there's some workloads that really don't care. But there's also workloads that care kind of a lot. You know, giving up 10% of your GPU performance for SSDs, at least in my opinion, it seems like a dumb trade to make. But, yeah, limitations of 10th gen. But anyway, yeah, so that's kind of what's going on with that, is just like, I don't know why Intel just didn't give 10, like... if 10th gen had 20 lanes, like you could still have this PCIe slot. Like, I mean, M.2 slot. It wouldn't run at PCIe 4.0, but it would actually function. So, yeah. Anyway, yeah. As it is, this M.2 slot only works with 11th gen CPUs. But like the problem I have with that is like 11th gen CPUs, however, because they have less L3 cache than their 10th gen counterparts, and they're also really expensive, aren't really good purchasing decisions, you know, especially because, like, not only did Intel reduce the L3 cache, they also made the memory controller have more latency. It's like, so first you reduce the cache, and then you slow down the memory controller. And it's like, oh man, like, literally going backwards. Right? Like, AMD has a high latency memory controller, so they have just piles of L3 cache to compensate for that, and then Intel's like, well, you see, we can't have, like, I get why they don't have a bunch of L3 cache, because on 14 nano, like, cache takes up space, right? And 11th gen chips are already huge, so I can totally understand why, but it's just, yeah, like, 11th gen chips are kind of they're just weird. And expensive, which is probably the worst part of it, is just like... And then at the end of the day, they also just, like... yeah, performance-wise, they're just, like, weird. Sometimes they're good, sometimes they're kind of awful, and then at the end of the day, they're also really expensive, which is, like... I really... Like, I would be totally happy to stick a 10th gen in this motherboard. It's just, yeah, you wouldn't have that M.2 slot. So, that's something to keep in mind. Anyway, let's talk about the power delivery. Man, 11th gen makes talking about Z590 motherboards just always suck so much. Because it's like, would I actually buy an 11900K? No. Absolutely hell no. I'd buy a 10900K and put it in a Z590 motherboard anyway. Because, like, there's really no other, like, there's really not much of a difference between Z590 and Z490 boards with 10th gen CPUs. In fact, there's a lot of Z490 boards that have this exact M.2 slot with the exact same configuration where it won't work without an 11th gen chip. So I really don't see as this, like basically it's like, you know, like you're just stuck with these two, which is what you'd get on a Z490 board anyway, because, like, 10th gen just didn't have the lanes. Like... That's not a motherboard thing, that's an Intel thing. So, anyway, let's talk power delivery. So here we have the VRM. MSI has now started including iGPU VRMs. There was a lot, like, I think for Z490, there was, like, a bunch of boards that MSI had where it was, like, mid-range motherboards with no iGPU power. And to be fair, I can kind of understand it, but the thing is, if your GPU, if anything goes wrong with your GPU, which on the list of things that die in systems, I'd say motherboards and, like, GPUs are way above everything else. Especially GPUs. Just like GPUs, because the thing you need to understand about a GPU is, like, a GPU is like a mini computer in and of itself. So their failure rate is just awful. So yeah, if anything goes wrong with your GPU by comparison to other parts, that doesn't mean it's, like, super high and you should be worried about it, but it's like, if something's going to die in a system, it's probably the GPU or the motherboard. It's not going to be your CPU. Yeah, because, like, you know, so if something does go wrong with the GPU, like, on a lot of MSI motherboards in the past, you wouldn't have an iGPU phase, and so it's like, even if you had an iGPU, you couldn't get display output because MSI just didn't include that phase. Well, now for Z590, they are including iGPU phases, so you don't have to worry about that. Down here we have system agent power. All the other minor voltage regulators are sort of in this area. I don't know which one's which, so we're just not going to bother with that. They don't really matter. Like, that's why I call them minor voltage regulators. Of course, they're critical to the functionality of the CPU, but they're not like, oh, you're gonna have your VCCIO VRM die. Like that's not a thing. Like your CPU will die before you break the VCCIO rail. Anyway, the rest of the VRM is all vCore. The controller is an ISL 69269, nice, running in 8+1+1 configuration. So we've got well, actually, there's no doubling going on, right? Like vCore is just a straight up 8-phase, iGPU is 1 phase, System Agent is 1 phase. But you'll notice that there's significantly more power stages and inductors than is necessary for an 8-phase, and that's because MSI is taking a PWM signal and basically feeding it into 2 power stages at the same time. And then basically you have 2 power stages acting as 1 giant phase. So that's what's going on with that, and, you know, there's not really anything wrong with doing this, as far as I'm concerned. Like, this would be a problem if you did it with, like, a 3-phase, potentially. And there's still ways to, like, design around it if you have a really low phase count, but it's just... Yeah, like, once you're up at 8 phases, doing this is completely fine, as far as I'm concerned. Honestly, even at, like, 6 or well, 4, I think you're kind of pushing it. But, yeah, especially at, like, higher phase counts, like 8 phases... running one PWM signal into multiple power stages at the same time is a really great way of increasing the VRM's power handling capacity without, you know, massively increasing the complexity of actually designing it. Mostly because you can skip doublers, right? And doublers don't really add that much complexity either, but it's just like, you can leave out that component. It really doesn't affect the performance. Like, I have motherboards with and without doublers, and just... if you have a properly designed VRM, regardless of what goes into it, you shouldn't really be looking at, like, voltage regulation issues, because voltage regulation is kind of separate from the power handling capacity until you get to, like, the extreme limits of what the, like, right up against the limits of what the VRM can handle, where it's like, well, actually, even then, the thing, like, your voltage regulation won't go out of whack until the VRM is basically about to die. Is kind of the situation you're looking at. So, you know, the two are very much kind of independent. Like, you can have a VRM that's very, very powerful and delivers garbage voltage stability, like the voltage regulation is trash. And then you can have a VRM that's really weak, but in the current range where it does function, it actually delivers really great voltage regulation. Anyway, there's nothing, so anyway, that's totally off topic. 8 phases is a totally good, like, VRM design, and running the PWM signal into 2 power stages at the same time just doesn't really have any real downsides. I'm actually really surprised that it's only become popular recently, because, like, it makes so much sense. You get more power handling capacity. It doesn't really cost you, like, there's no, yeah, you do have to pay for the extra power stages and the extra inductors, but, like, you don't have to pay for the doublers. So yeah, I'm really, and actually, like, there have been motherboards in the past that did this. It's actually, like, anyway, doesn't matter. Like, this is an 8-phase PWM signal going into 2 power stages at the same time. So we've basically got, like, gigantic phases. And really, like, the annoying thing is, like, phase count is really kind of disconnected from the overall, like, you can have a really weak 16 phase, you know, if you just use, like, 20 amp power stages. I don't know why you'd want to do that, but you could. Wouldn't be very good. Anyway, the power stages that MSI is using here are by no means weak, as they are RAA 220075s. These are Renesas 75 amp smart power stages. So these are called smart power stages because they integrate current monitoring and temperature monitoring and a bunch of safety features like short circuit protection and over temperature protection and over current protection and yeah, all kinds of fun stuff like that. And you can get components that don't integrate all of that stuff, which just makes designing the motherboard more difficult. But on the flip side, the components are cheaper, so... Yeah, but anyway, the other thing is 75 amp smart power stages. This is like a super weird current rating, right? Like, we've got 70 amp parts, 80 amp parts, and it's like, do you really need a 5 amp step between the 70 amp parts and the 80 amp parts? Apparently we do. Either way, these have very similar performance to all the other like 70 to 90 amp smart power stages that you see from most manufacturers. So all that really means is that with 16 of them making up the V-Core VRM, this motherboard is really, really powerful. We're looking at this kind of like these kinds of efficiencies for the VRM itself. Now this is accounting just power stages and the inductors, not power plane loss. So basically just the heat output of this part, like, well, this part of the VRM, because there's obviously power loss going from the VRM to the actual CPU, and there's no way to really, like, for me, there's no way to really account for that in these PCB breakdown videos. So anyway, in terms of efficiencies, 200 amps, so for like regular cooling, well, not even regular cooling, like to hit 300 amps, you need quite a water cooling loop, potentially direct die, yeah, actually you'd probably want direct die for that. Like this is really hard to hit without absolutely insane temperatures. So anyway, in the sort of water cooling, operating range, we have VRM being slightly below the peak of its efficiency curve to right at the peak of its efficiency curve. So this VRM is actually very, like, a good fit for, like, 10th gen CPUs and 11th gen, like, the highest end 11th gen and 10th gen CPUs, right? 10 cores, 8 cores. Yeah, this VRM will have absolutely no problem powering any of those. And then for LN2 overclocking, I mean, you're going to get away with this. Because the thing is, for LN2 overclocking, the benchmarks, like, you're not going to run an hour of Prime 95 on liquid nitrogen. Nobody does that. You're going to run Cinebench, and Cinebench finishes in a couple seconds. And since it finishes so quickly, like, the VRM doesn't really have time to overheat. So yeah, like I said earlier in the video, like if you wanted to do LN2 overclocking on this motherboard, it's not a bad option for that. Like you do have the postcode, you even have the K-type thermocouple thing, which again, I've not really seen anybody use, but it's there. And the VRM is more than powerful enough for anything you want to do. So yeah, really just all around very, very solid motherboard. So that's what's going on with the power delivery. And then in terms of the output filtering, MSI is using a bunch of Nippon Chemicon aluminum polymer capacitors rated for 10,000 hours at 105 degrees. And then they also have some of these little extra multi-layer ceramics before the socket, like on this side of the socket, which I'm not sure how much of an effect they have, but they do have an effect, otherwise they wouldn't bother including them. What's still interesting to me, though, is that MSI motherboards tend to have a really, like, this isn't as empty as some of the other boards from MSI, but they do tend to have a kind of less dense capacitor configuration in the CPU socket itself. Either way, I actually did voltage regulation testing for the Z490 Unify, and that actually uses a very similar VRM, actually almost the exact same VRM configuration as this. And it did great. I mean, it had a little bit more voltage overshoot, and if you maxed out the LLC, it started to actually show some, more significant amount of undershoot compared to, say, Gigabyte and Asus Z490 motherboards. And by Asus motherboards, I mean literally just the Maximus 12 Apex. So I didn't test any, unfortunately I didn't get a chance to test any other Asus Z490 boards. But yeah, so in terms of voltage regulation, like this VRM configuration that MSI has, like it looks very normal. It doesn't look like they're doing anything very special, but it works really, really well. So yeah, I just, from testing, there's no issues with this. Like, it doesn't look impressive. There's not like, oh, they're putting tantalums in interesting places or using super low ESR, low ESL capacitors. It's just kind of like on paper, I'm surprised that this works way better than it looks, is one way to put it. So yeah, and like the important thing is that it works really well, right? So yeah, in terms of voltage regulation, it matches other top-end boards. It does have well, the Unify had a smidge more overshoot, but the Unify, I think, actually has even less socket capacitance than this does, and it was only like 10, 20 millivolts, and voltage, like overshoot in terms of voltage regulation, isn't really concerning from an overclocking perspective unless it's really, really, really bad. Because the only real concern with it is that it could cause degradation of the CPU. But in order for that to actually be a concern with overshoot, you'd have to be looking at, like, you know, ridiculous amounts of overshoot. Like, way, way more than what you'd be getting on a board like this from MSI. So... yeah, that's why, like, that's why when I do why when I do voltage regulation testing, I just kind of gloss over the overshoot figures. With the exception of there was one motherboard on Z370 that was hitting, like, I believe it was hitting like 1.7 volts or something on load release, which was like, oh yeah, that's probably bad. But yeah, this is by no, like, this was doing great in like, well, a very similar VRM, not this specific VRM, but a very similar VRM configuration from MSI was doing great. So I see no reason to be concerned by what MSI has done here. Interestingly enough, MSI also has very, like, normal looking input filtering. We only have 4 270 microfarad capacitors on the input filter, though they did distribute them around the power plane. To just make sure that, you know, you don't have, like, phases all the way over here trying to grab current from over there. Because there are some motherboards out there from a certain vendor that I'll not name. Or actually, I'm not even sure if it's that specific vendor, but it's not that uncommon that you'd see motherboards where all of your bulk input filtering is over here, and then it's like, okay, that's great, but when these phases down here turn on, where's that current coming? Like, where's that current coming from? Well, it's over here. So that obviously isn't exactly ideal. So yeah, there's not a lot of input filtering capacitors, but they are at least distributed around the board. And also the multi-layer ceramic configuration for the input filtering is actually, I'm not sure, like, I think these are input filtering, which is kind of, like, if those are, that's kind of unique. I don't think I've seen that very often. I'm pretty sure they have to be input filtering. I can't think of anything else that they would be. At the same time, they don't look like they're wait, no, because that would be 12. I'm very confused what's going on there. But yeah, and then of course, like, the thing is, this is just standard for motherboards, is to have multi-layer ceramics directly behind the power stages, because these will be going between the ground pad. So power stages normally have a middle pad that's ground, or roughly middle pad on the package that's ground, and then there's another pad that's going to be 12 volts. And so this pretty much, like, this side is going to be like the ground side of the power stage. This is the 12 volt side of the power stage. Oh, actually, no, it is doing that. Yeah, because that, yeah, so you'd have, I guess it does this. So you have, yeah, so this is probably 12 volts over here. Anyway. Oh, so they have some smaller ones for input filtering, which you don't normally see on the back. I'm not sure that's very significant, though. Anyway, so, yeah, just very similar. Like, this is a very similar VRM to what MSI had on the Z490 Unify. The Z490 Unify VRM worked really, really well. This is basically the same thing, except they've got rid of the doublers, which doesn't really make much of a difference. Well, it makes a difference for MSI. It makes the VRM cheaper to manufacture. In terms of performance, it really doesn't make much of a difference. And they replaced the 90 amp power stages with 75 amp power stages, but the actual, like, usable, like, in the actual real world operating range where you'd be running these power stages, it still doesn't make a difference, right? Like, this is why, like, the 70 amp power, like, from 70 amps to, like, 100 amps, the smart power stages all have very similar performance curves. So it's just like having a motherboard with 90 amp parts or 75 amp parts, it doesn't really make much of a difference. So yeah, very, very solid VRM here from MSI. And yeah, let's move on to the memory section, I guess. So for memory, the motherboard uses a 6-layer PCB, which I guess you could kind of include that in the power delivery section as well, the fact that this is a 6-layer PCB. Because, like, that gives you more power plane to work with, and that obviously improves power delivery to the CPU socket. But the thing is, I haven't figured out how to mention it twice. Because it's relevant, like, having a 6-layer PCB is relevant to both the power delivery and the memory layout. But yeah, anyway, 6-layer PCB, we're looking at a tabbed daisy chain topology, which MSI was already doing on their Z490 boards. And since it is a daisy chain, though a kind of special one, your preferred DIMM slots are these two. Fun fact on MSI motherboards, like, first of all, the board just bloody tells you that you should use, you know, this slot and this slot first. But the other thing is, MSI motherboards, if you do use the wrong DIMM slots, they'll actually give you a warning when the board first boots up that your memory is in the wrong DIMM slots. So that's pretty neat. Anyway, yeah, so daisy chain topology, so you have to use the outer DIMM slots, because if you don't use the last DIMM slots in the chain, you end up with reflections coming off of the unterminated traces hanging off of the, like, basically when you have a signal going like this, well, if you have a signal going to like this slot first, because like high-speed electrical signals start behaving a bit like waves, that signal will kind of carry on past the DIMM slot that it's going to, and then it'll bounce off the end of the pins in the last DIMM slot. And basically, if you use the wrong DIMM slots on a daisy chain, the memory, like, honestly, sometimes you can't even boot JDEC settings. It's really bad for signal integrity, and so you just can't run any reasonable clocks. And that's why daisy chain motherboards will always have an indicator like this telling you to use the correct DIMM slots, because if you don't use the correct DIMM slots, they barely function. Now, if you have, you know, 4 memory sticks in the board, this isn't a problem anymore, because the memory sticks actually have a bunch of like termination resistors on them, so that they can deal with that. So you no longer have a problem with that. And then you have the problem, like the weakness of daisy chains when you have them fully populated is actually that the signals travel to some of the DIMM slots faster than to the other DIMM slots. But that's easier, like, that's somewhat easier to account for on the memory controller than just having, you know, the signal integrity be terrible. So timing differences can be dealt with. The signal being a mess can't be. Okay, so anyway, speaking of the signal being a mess, that's what the tabbed daisy chain is supposed to deal with. So you'll notice that these memory traces up here look very funky. They almost look like they're going for a carbon fiber texture, but that's not what they're doing. What they're actually doing is, if you have your memory traces something like this, these traces have little tabs hanging off of them. And the actual tabs on the board are more like trapezoidal shape rather than little lines hanging off. But I'm not going to be drawing, you know, little rectangles here, because that would take forever. And the idea behind putting these tabs on the memory traces is that when you have high-speed signals traveling near each other, once they get to the end of the trace, they can actually sort of cause interference with each other. And so by adding these tabs to the traces, actually, I'm not going to try to explain this. Unfortunately, this, like, I've tried to read the paper about why this works. It's just, it goes over my head. It is way too far into, like, electronics engineering. Yeah, I don't actually get it. But the purpose of this is to reduce far-end crosstalk, which is basically interference between the traces due to the high-speed signals going through them. Why high-speed signals cause interference, I'm not going to try to explain, okay? Because that's the part where it's like, yeah, I'm not an actual engineer, so not an actual engineer, so I don't get that part. But basically, this is supposed to help with reducing far-end crosstalk, and so you can run higher memory speeds, and that's the theory behind doing this. So, yeah. And MSI has done this on Z490. There, it seemed to work it worked great. And so they're doing it again on Z590, because if it works, why don't fix it, right? Anyway, so in terms of memory configurations that you'd want to run, obviously this being a daisy chain, it favors 2x, you know, like, well, anything two-stick configurations. Basically, the only scenario in which you should be fully populating all of the DIMM slots on this motherboard is if you want to hit 4 times 32 gigs. That is the only scenario where you should be getting 4 memory sticks for this motherboard. Otherwise, you should get 2x16 or 2x32, because 4x8 is going to clock worse than 2x16. 4x16 is going to clock worse, and like significantly worse. Depending on which flavor of 4x16 you end up with, it could be anywhere from like somewhat worse and way worse. Okay, like it's your 4x16 on a daisy chain topology it basically ranges from kind of bad to horrible in terms of overclocking capabilities. So you really don't want to be running 4x16 if you can avoid it, and you can, because 2x32 kits exist, and this is a dual channel platform. So this is sort of the memory configurations that you'd actually want to run, and this is like if for some reason you need 128 gigs of RAM. Yeah, that's the only time you should actually be populating all 4 memory slots. Otherwise, don't do that. And yeah, that is it for the MSI Z590 Gaming Force. Really cool board, you know, very, very capable VRM on it. We've got a postcode. That's basically all I care about. It's like, you know, cheapest motherboard in MSI's lineup with a postcode. Very capable VRMs, not going to have issues powering anything that you can put into the socket. Yeah, that's basically it. Other than that, it's like I don't feel like there's anything super special about this board otherwise. Because, yeah, you've got some PCIe slots, some M.2 slots, you've got 6 SATA ports, there's fan headers, you know, the usual stuff that motherboards come with. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, and, you know, the usual YouTuber merch. Both of those help out immensely with running the channel, so it would be much appreciated if you check them out. And that is it for the video, so thank you for watching, and goodbye.